recording now. Yeah. Okay, so we're reviewing Einstein solids first. So if you're watching this asynchronously, you can come back and read this some more. So an Einstein solid is effectively just something where, again, like the idea of buckets and particles, you have a bunch of buckets which correspond to the oscillators, and they can hold some number of, I don't know, energy units, whatever you want to throw in there. So the way that we pictorially demonstrated how to calculate the multiplicity for an Einstein solid was we said, okay, an easy way to think about this for an Einstein solid is that we can pictorially think of it as energy units are represented by dots. So we'll call that an energy unit. And we'll use bars to divide between the different oscillators. So basically, if you want to graphically say the state of an Einstein solid, you can write it, the microstate of an Einstein solid, you can write it as just being like one energy unit here in this oscillator. So this denotes a single oscillator, and this denotes the difference between that oscillator and another oscillator. We could put 3 units of energy in this one. We could put no units of energy in one right here. And we could put 4 units of energy in one over here. So basically, this is oscillator 1. This is oscillator 2. This is oscillator 3, and this is oscillator 4. And graphically, we can use these dots and bars to denote every single microstate of this Einstein solid that is made up of 4 oscillators. So another way to say this is that every possible arrangement of these dots and bars corresponds to a valid microstate, right? So notice there are Q dots here. We'll just call Q whatever the number is of dots that we put in. And there are n minus 1. So if we call this, let's say there are n oscillators and Q energy units. So if we're talking about n as referring to the number of oscillators and Q is the number of energy units available, this case right here is specifically that n is equal to 4 and Q is equal to, what is it, 1, 2, 3, 4, 5, 6, 7, 8. Okay, but notice that we only need to use 1, 2, 3 of these bars in order to note this arrangement right here. So there are n minus 1 bars. So there are Q dots plus n minus 1 bars, and we want to choose Q of all of those symbols to be dots. So this is total number of symbols that are available to us, or spots here. And in order to uniquely describe the microstate, we have to choose Q of them to be the dots, right? Because there are 8 or Q energy units that you need to choose here. So remember the language of binomial coefficients. So we want to choose, so if we write the binomial coefficient as the following, so as we write it as Q plus n minus 1, Q. What this says, remember, if this is the binomial coefficient, it says Q plus n minus 1, choose Q. So it's basically you have Q plus n minus 1 things that you want to choose Q of them to be something. So you can map the language of the binomial coefficient directly onto how you can specify the microstate of an Einstein solid using the binomial coefficient. So that's how you get from Einstein salad to binomial coefficient in a nice intuitive way. And recall that the binomial coefficient can just be written as q plus n minus 1 factorial. So it's just this number factorial divided by q factorial times n minus 1 factorial. So this is just the general expression for an Einstein salad. Multiplicity for an Einstein salad of n oscillators and q energy units. Einstein salad multiplicity. So I think I remember a lot of people being confused about, especially when we talk about like Einstein salads where you have like one Einstein salad and another Einstein salad and they're interacting and you want to calculate like the total multiplicity. I remember people having a lot of issues with that. So I made a note that figure 2.4 on page 27, or sorry, not page 27, page 57, I think, of Schroeder is a good example of exactly how this works out. So let's just go there. So basically, if you're looking at page 57, what Schroeder is considering here is that you've got, you have two Einstein solids. First one has 3 oscillators, and the second one also has 3 oscillators. So you got system A and system B, and they're taken to have some total amount of energy that can be distributed throughout both of them. So that's just always going to be QA plus QB is equal to 6 is conserved. So the figure 2.4, the table to the left of the figure, is the one that I'm talking about now. So goes through and nicely calculates the total corresponding to every single macro state, and then also at the bottom uses another formula to calculate the total number of microstates of the total system. So if I were to ask, what is the total number of macrostates for the entire system? How would you calculate that using this formula before? Anybody? N equals 12, Q equals 3. Where did 12 come from? So let's just rewrite this. So omega of n comma q. It's okay. This is why we're doing this. Plus n minus 1 q. This is q plus n minus 1 factorial all over q factorial times n minus 1 factorial. So if you consider the system as a whole, it has what? Well, it has n is equal to NA plus NB because it's made up of both A and B. So it's got 6 oscillators, right? I don't know if anybody can hear my cat, but he will not shut up in the background. So Q total here, I'm just going to call Q. Again, it's just given as 6. So in order to calculate the total, just plug both these into here. And yeah, that makes sense, right? Yeah, so for this case, omega of 6 comma 6 is just equal to 6 plus 6 minus 1, 6, which if you calculate it using the form of the binomial coefficient should end up being what he lists at the bottom, which is 462. Okay, so there's confusion here when it comes to calculating the total number of microstates available for the entire system versus for each part of the system. So there's another total that comes into play here. So specifically, if I consider a specific macro state, so what is omega total for, let's just say QA equals 0 and QB equals 6. So now I'm specifying a specific macro state of the system. Up here, I would have been asking for the total number of multiplicities of all macro states. So if I want to calculate this, well, what do I have to do? Anybody? I'm still going to use the same formula, but I'm going to use it twice. Does anybody remember? So multiply the two together. Yeah, so remember the way that you get total multiplicity if you're talking about two systems that are interacting is you're going to find the multiplicity for A, take it times multiplicity for state for B. So we just need to find what these are. So for A, it's in this state right here, and it's got 3 oscillators. So let's take NA equals 3 and QA equals 0 and calculate what that is. I guess I could have written that in the multiplicity function. So yeah, sigma sub A, sorry, omega sub A is equal to, this should be N, which is 3, and this should be 0. So if we do that, plug it in, what do we get? We've got 0 plus 3 minus 1, 0. That's going to be, so that's 2. So this is 2 factorial all over 0 factorial times 3 minus 1, 2 factorial. What's 0 factorial? That's the only thing that, yeah, 0 factorial is 1. So obviously the multiplicity for it to have no energy, well, there's just one way, right? So we've got A. Now let's also calculate B. I'm sorry if this is getting a little messy. So if we've got state B now, it has as well, also has 3 oscillators, but it's got 6 units of energy. So we use the exact same formula. So it'll be 3 plus 6 minus 1, 6. So this becomes what? 9 minus 1, 8. Writing this up here. So this is going to be what? 8 factorial all over 6 factorial times n is 3, so 2 factorial. I think I have that right. If I did that right, this should come out to 28. And so overall, omega total is just equal to 1 times 28. So there are 28 ways to arrange the total system such that it has this specific macro state. Now, what I could do is I could cycle through every single macro state. So I could go QA equals 1, QA equals 2, QA equals 3, on and on to 6. And I could calculate the total multiplicity for each of those macro states. And if I add them all up, doing it this way, you should also just get 462. So I would say if you're confused about how to do this, how to break it up into the two systems themselves versus considering it as a whole system, that you should go through this and just kind of confirm it for yourself. Okay? So you should be able to add all up all the individual multiplicities for each macro state to get this total multiplicity right here, 462. And that's just exactly what he has written on page 57. So does that help people? Does that make sense? I don't know. I can't see any faces because I'm sharing screen, so yes, sir. Okay, if this doesn't make sense, talk to me about it some more, and we can figure out what's going wrong, but hopefully this helped. Okay, what's up next? We've got a bunch of sticky notes through my notes. Okay, so we got through that. Let's see. Ah, yes, you wanted to review heat engines and refrigerators, right? Am I right about that? Do we want to hear heat engines and refrigerators quickly? Maybe not too quickly, but let's see, how far should we go exactly? Yeah, so and refrigerators. So I think that people understand the basic concepts of what a heat engine is and what a refrigerator is. I think what people struggled with was identifying what heats they're supposed to calculate and where they correspond to on like a PV diagram. Am I hitting on a good point there? Is that what people are confused about? Yeah, okay, that's what I figured. So, okay, so let's talk about a heat engine first. So a heat engine, just to, not to beat a dead horse or anything, but what a heat engine is just think of it as some black box, right? You've got some hot reservoir right here, and you've got some cold reservoir over here. Calculating the QC, QH, and work from PV to RMs. Yeah, trips you up. Yeah. I will give you a step-by-step process by which you will never screw it up ever again if you follow it. So work comes out. QC for a heat engine is the heat that goes out of the gas and into the cold reservoir. QH is the heat that goes into the gas from the hot reservoir. So basically, let's take like let's take the PV diagram from the previous exam. So it looked something like this, if I'm recalling correctly. So it was PV. Oh, what did you have? You had like an isothermal, or sorry, adiabatic compression, I think. And then you had an isothermal compression. And then you had an isobaric, isochoric, sorry. Was it isobaric or isochoric? I think it was isochoric. So I think it went like this. Am I right about that? Okay, cool. Good, good, good. So it was like A, B, C. Okay, so if I'm told, hey, this is a heat engine, you need to calculate the efficiency. I'm thinking, okay, I can calculate the efficiency. I know that just basically using words, first of all, the efficiency of a heat engine is just, we can think of it as like the benefit all over the cost. And we had showed before that basically the benefit that you get is the work that you get out, and the cost is just the heat that you have to put into the system, into the gas. So you can also express this as breaking up the work into QH and QC. Since energy is conserved, it must be the case that work is equal to QH minus QC all over QH. And so therefore this should become like 1 minus QC over QH. So you can either think about it this way and calculate the work, or you can think about this way and just calculate the heats. So basically, the problem of every single heat engine, if you've got a PV diagram and some processes and you've written them down correctly, boils down to how do I calculate QC and QH? Okay, well, QC is going to be the heat corresponding to this diagram whenever heat is leaving the gas. Okay, so let's think about that. Well, where is heat leaving the gas? So let's start at A and go to B, and then we'll go to C and to A. So from A to B, is there any heat leaving the gas? if this is adiabatic, sorry. Right. So anytime you have an adiabatic process, right, Q is equal to 0. So no heat is going into the gas, no heat is leaving the gas. It's just nothing. So nothing can be contributed from A to B for QC or QH. All right, cool. What about from B to C? So what we're doing here is we're starting off at some volume V, and we're compressing to C while keeping the temperature constant. So generally, if you compress something, will the temperature go up or down if you're not holding it constant in some way? Yeah, so Deb's got it. So basically and intuitively, since you're going from B to C and you're compressing this gas, since the temperature is staying the same, heat has to be leaving, right? Going from B to C, if temperature is staying the same and you're compressing it, heat has to be leaving in order to keep the temperature the same. So what heat do we think should correspond, what heat should B to C correspond to if heat is leaving the gas? QC, exactly. So yeah, so go through it like that. So you know what, this process right here, heat is leaving the gas, so that's going to correspond to QC. It might be the case that you have some other kind of diagram where there's also other processes where heat is leaving the gas, but on this one, this is the only process. So heat leaves there, and since we're going from this point to this point, heat can only be entering at that point because effectively you're going in between two different isotherms. If you were to like span this by a bunch of isotherms, like this is some temperature, this is another temperature, this is another temperature, and it's an increasing temperature. So if you move up the isotherms, you've moved up in temperature, you must have added heat in this point. So basically QC corresponds to there, or sorry. QH corresponds to there, and QC corresponds to there. So now that you've got nailed down exactly what processes correspond to what heats, all you need to do is actually calculate those heats. And so the way to do that is just think about exactly what kind of process is happening during each of these different points right here. So from like B to C, can we say that QC is work done from B to C? Yes. So yeah, that's exactly what I was just about to get to. So I'm trying to break it down into steps that you can take in order to determine how this works. So now that you've determined which processes QH and QC come from, now look at these specific processes and say, well, what can I say about them? Well, if this is isothermal, what does that tell me? That tells me that delta U, the change in energy, is equal to 0. And if we don't remember why that is, remember that we can write U as NKT times F over 2. Forget about the F over 2. The T is the only thing that can change. So if we're isothermal, delta T is 0. So delta U is 0. And first law of thermodynamics just tells us that the change in energy is equal to the work done on the system plus the heat that is added to the system, right? So if we know this is 0, we've done this 1,000 times, Q is equal to minus the work. So you just calculate the work, you got it, okay? Similarly, from C to A, this is at constant volume. So you just have to calculate the change in energy in going from here to here because the work is 0. And then you equate that to the heat and you're done. Cool? Is that helpful? So let me write this out again. So basically, steps for heat engines. Step 1. Look through every single process. So go from point to point on the diagram. So like start at A, go to B, and determine when heat is entering or leaving. So if heat is entering, then that corresponds to QH. If heat is leaving, then that corresponds to QC, right? And then basically step 2 is just do thermo So it's effectively a two-step process where this involves multiple steps. Yeah. Yes. Yes. Yeah. Well, so yeah, be careful because like, yeah, these QC and these QHs are defined as the heat going into the cold reservoir or the heat going into the or the heat going into the gas from the hot reservoir. So they have the minus signs built in. That's a good question. Work is equal to minus PdV. Yes. Yes, it is equal to minus PdV. But yeah, so this process right here, C to A, so the work is 0, right? So if the work is 0, then you still have the first law of thermodynamics. So you always have, in general, that du is equal to W plus Q. If you're going from C to A, well, W is 0. So this is just equal to Q, du equals Q. So now the only expression that you have to calculate is this du, the change in energy. And the way that you would do that is in the solutions online, but just a little sketched out. So basically you would take the equipotential theorem to write this result, du. So you could write it as F over 2 nk delta T is equal to Q. Well, then you just need to figure out what the change in temperature is. So you can find this temperature and you can find this temperature by knowing that this is an adiabat and using like the adiabatic relations in order to actually find what delta T is in terms of other stuff. Are we good? So are the W and QH in the expression for E the absolute values? Yes. Yes, they are. You all good? Oh. Right. Okay. Oh, and I guess I skipped refrigerators, but it's basically just the exact same thing in reverse. So, yeah. So a refrigerator is something where you do what? You take work, you put it into the system, it allows you to get heat. We call this QC. We call this Q. Uh-oh, my internet connection is unstable. Sounds like you are tired. Hello? Can anybody hear me? You can hear me? Okay. Yeah, it said my internet cut out. No, I'm not tired. I've already had like 2 cups of coffee, so there's not a chance I could be tired. Okay, hopefully the internet doesn't cut out again for the last little bit. So I was just saying, here's the diagram of a refrigerator. So this is heat engine. Blame the cat. Yeah, I wouldn't be surprised. It's little spies, right? So yeah, this is a refrigerator. You put work in order to suck heat out of the cold reservoir and into the gas and then dump heat into the environment, right? So for refrigerators, the relevant thing that you want to calculate is what? Anybody? Yes, it is. It is the coefficient of performance. Yeah. So you're asking how do we know that heat flows from the refrigerator to here? First law of thermodynamics, or sorry, not first law, second law of thermodynamics. There has to be some non-zero heat displaced into the environment in order to account for the heat flowing into here. It's not possible to like just pump energy into the gas forever. Why would it flow? Because what ends up happening is that this compartment right here gets hotter than the outside environment, and so heat will favorably flow from inside the engine to outside of the environment. So like this temperature in here will be greater than this temperature out here. Yeah, not a problem. And likewise, the way engines have to work is like when the heat is actually transferred to the cold reservoir, the interior of the engine has to be colder than the outside for heat to flow to the outside, to the cold reservoir. But yeah, so the relevant thing for refrigerators is the coefficient of performance, which is, again, basically just the benefit over the cost. Here, the benefit is the heat that you're able to suck out of the cold reservoir. In this case, think of it as just like the inside of your fridge, over the work that you have to put in order to actually make that happen. This is like the electricity that you consume. So again, you can break up work into QH minus QC. And you can do, oh, sorry, there's a C there. You can multiply by, what did we do before? Like 1 over QC times 1 over QC, but yeah, don't worry about that. So if you've got these two expressions, you're good to go. You can either do it this way, calculate the work, or you can do it this way and calculate both the heats. But now you just do the same thing. You look at the diagram and you say, okay, where is my gas heating up? Wherever it's heating up, that's going to be the heat corresponding to QC, because that's the heat that's getting dumped into the gas. Look at all the processes. Where is it heating? Where is it losing heat? Well, wherever it's losing heat, that's QH. So calculate QH and QC then, just using whatever you know the processes to be, and you're good to go. So it's the exact same process as the heat engine, just everything's flipped around. Okay. So hopefully I'll be able to make up another fun heat engine problem and everyone will get it this time. Okay, last bit of review that was requested was talking about, is basically the chapter in Schroeder where it was titled Free Energy as a Force Toward Equilibrium, which is effectively when we talked about systems that are in contact with a reservoir and rehashing the second law of thermodynamics in terms of the relevant quantities of the system itself. So basically, what happens when systems aren't isolated? Like, how does their second law of thermodynamics change if they're in contact with these specific systems? So let's go through that quickly and just kind of remind ourselves. So the way we're thinking about this is we've got some system. Let me make that bigger. So this is our system, and it's in some large environment that is just filled with stuff. Might be at constant temperature, might be at constant pressure, who knows, who cares, but it's in contact with some large thing. So overall, this entire thing constitutes a closed system. So the second law of thermodynamics will surely hold to the whole thing itself. But what we want to do is we want to understand the second law of thermodynamics just in terms of the system itself, using the fact that we know that the whole thing is a closed system. So how do we do that? Well, we can say that the total entropy is just going to be equal to the entropy of the system plus the entropy of the reservoir, because those are the only two things that exist here. And likewise, we can say that ds total is equal to ds plus ds reservoir. So this is all just basic results of the fact that this is a closed system. Now, if we assume that only energy flows, then we have the thermodynamic relation for the total entropy, ds plus dsr, and we can relate the second one, if we want to 1 over T sub r dur. So in going from here to here, we're just using the thermodynamic relation for the reservoir. Do I have that written? Yeah, I do. ds equals 1 over 2, 1 over t du plus p over t dv minus mu over t dn. So yeah, Jacob, you got a question? Well, we're not actually just focusing on the change in entropy of the reservoir. Where do you see that? Did I say something? Oh, okay. Yeah, so the idea is that what we want to do is we want to describe systems that are like relevant to our experience. And so whenever you're doing like chemical reactions or something like that, um, you're almost always wanting to consider things where you have some kind of system that's like this. Like you've got some small thing that's taking place and it's in contact with the entire universe or a vat of something. So the reason we're focusing on the system itself, like rather than the reservoir, is just that it's relevant to our experience. That's all. Like none of this is necessarily fundamental in any shape or form. It's just like stuff like this is relevant to us. Does that answer your question at all? Yeah. Okay. I mean, you could absolutely reframe everything in terms of the reservoir itself, but like basically what happens is like you don't want to care about the reservoir. You don't want to have to think about the reservoir. You just know that it's there and you only want to think about the system. So this says, well, how do I do that if I know it's a big old closed system and I just want to care about the system? So yeah, so going from here to here is just using the first law of thermodynamics as applied to the reservoir and assuming that only energy flows. So you can get this expression. And at this point, you just got to remember that, of course, the total energy is conserved. And therefore, what do we have? We've got du plus dur is equal to 0. So that tells us that dur can be expressed in terms of the system change in energy, just the negative of it. Right? So whatever the system gains, the entropy, the reservoir loses, and vice versa. So we put that expression in here, plus, hold up. What did I do here? Oh, yeah. And then another thing, obviously, is that we're assuming that the system is in equilibrium with the reservoir, and the reservoir is at temperature T. So reservoir temperature is the same as system temperature. So plus 1 over T minus, right? Yes, du. And we can just pull out an overall minus 1 over T du minus T ds. So this is just the expression of the total change in entropy in terms of quantities only in the system itself. And so we recognize this piece right here as just dF, where F is the Helmholtz energy. So this just says that the expression of the second law of thermodynamics, if we only focus on the system, can be expressed as the following. So if the second law of thermodynamics holds, which it does, and entropy can only increase or stay the same, then that means that if you express it in terms of the system, and the system is at constant temperature and only energy is flowing, that the system's Helmholtz energy can only decrease or stay the same, right? It's related to minus 1 over T dF. So if dF decreases, that corresponds to the total entropy increasing. So hopefully that cleared up a little something. And now we can just do the exact same kind of thing, but now let the system also exchange volume with the reservoir. So basically you get, you still have this same expression right here, But now in going from DSR to this point right here, we're not going to assume that dV is 0. We're only going to assume that dN is 0. So you just pick up an extra term on this side right here. So let's just say if energy and volume flow, whatever volume flowing means, but you get the idea. Then ds total is just equal to ds minus 1 over t du minus p over t dv. And this is all from the thermodynamic identity. But this can all just be expressed as minus 1 over t times du minus t ds plus p dv. And this is just the differential of the quantity that we had defined earlier, which is g, the Gibbs free energy. So if you are in a system like this, where you're in contact with a reservoir that has constant pressure and constant temperature, then the second law of thermodynamics just translates into wanting G to either stay the same or decrease. So this was specifically like one of the problems on the previous exam. It was asking you to decide which way the reaction went. So if it specifically said in the problem statement, like consider a system that has constant temperature and constant pressure. So in that case, that translates into this. Does that clarify anything or solidify ideas? That's really all that's going on there. There's not really too much more I can say, I don't think. So basically, like, all you're doing is translating the second law of thermodynamics into what it looks like for the system when it's in contact with some kind of reservoir. Is that cool? Does that help? Effectively, it comes down to decrease in usable energy as S increases. Yeah, that's right. This S increases, the amount of usable energy decreases. And thus, if the second law of thermodynamics holds throughout the universe, eventually it will all just be nothing. So what's the point? Is everybody good? It's not depressing, but yeah. Realize that all of these timescales are so enormous that it doesn't matter. And who knows? There might be other interesting phenomena out there where, you know, at some point in the future, what was it, from the story that I put on the first exam, did anybody, I think Deb was the only one who ever said they read the first Isaac Asimov short story that I attached. If you haven't read it, Jacob, you should read that. Maybe you'll be a little bit less depressed. It's obviously sci-fi, but it's still fun. Go read it, okay? This is all I have for you. It's been a great time having you all in class. Yeah. So that's all we got today. I will, I guess, I'll record like a little segment on blackbody radiation. Expect that to be maybe like a 20-minute or so conversation. Can we get a yeehaw? Yeehaw! Is that something like all the other professors do at the end of the semester? That's the Grinnell way? End it all with a good old yeehaw? Okay. Yeehaw. Take it easy, everybody, until the exam. Everybody does it. I find that hard to believe. I think you're just screwing with me. But yeah, have a great rest of your semester. Good luck on the exam. Talk to me on Monday if you want to. And also, don't forget to fill out the course evaluations. I'll probably start nagging everybody again right after the final, but God knows taking it after the final is always the worst idea because everyone's going to be grumpy after taking an exam. So yeah, just get those filled out. I'll get all your homeworks graded in the grade book, and you'll have like a tentative grade before the final. So just make sure you look over the grade book and make sure everything is correct. If you have any discrepancies, I'll be available all weekend and on Monday. All right. So thanks for a great semester, everybody. You've been great students, and I'm sure you'll go on to do great things in the future. Contact me if you ever want to, but yeah. Yeehaw! See ya.